Friesecke James Muller theorem. So that if we have omega, which is a Lipschitz domain, it doesn't matter what it is, it just means it's a nice domain. P is bigger than 1, omega is contained within Rn. There exists a constant C, which depends on n, p, and the domain, such that all smooth functions, so smooth in this case only needs to mean that it's C1. The full statement is for Sobolev functions, but there's no real loss of generality here. We have that the infimum of all rotations of the integral of omega of the gradient away from this rotation to the p dx is less than this constant times the integral of the distance to the power p of the gradient away from the space of rotations. Like this. So this is the picture, this is the space of rotations, and we have that the hypothesis is that the gradient lives in an LP sense close to this set, that as we move around x, the gradient is moving around like this. Yeah? And the conclusion is that it's actually close to one particular fixed gradient with the same control. So this is, as I was trying to indicate on the last class, a kind of remarkable result. And I sketched how you can start to begin to get some kind of control from elementary methods. So if this thing was of order epsilon, then by doing these kind of looking at lines and their inverses, you can get this down to be some kind of root power of epsilon. But it was a method that was losing lots of information, losing control at lots of stages. And that's not how this theorem is proved. So, to prove this, Friesecke James Muller used some of the ideas that we use to prove this absolute version of Liouville's theorem. In particular, they used the underlying PDE in an essential way. So, we're going to prove in the special case for n equals 2, and we're going to assume that u is the gradient of u is bounded by some absolute constant. Let's call this constant C1. And for certain reasons, this is not a particularly difficult. This assumption you can justify without too much difficulty with the use of some truncation result. N equals 2. It's just for the ease of drawing pictures mostly. Yeah, these are the assumptions we're going to make. So, and we're also not going to pull the full strength. We're going to show that if we have some initial region, we can find a subregion inside where the integral of the gradient away from a fixed rotation in the subregion is the same order of control. So we're going to prove a cut-down version of this theorem, but still prove the heart of this theorem. So, how should we begin? Well, what do we have in play? We have something that is living quite close to a set of rotations, and we know that if it is on the set of rotations, then we can actually have an underlying harmonic PDE. So we're going to do the following thing to begin with. So recall the following thing. So we know that the divergence of the cofactor of any gradient is equal to 0, like this. Okay. And if, say for any w, and we know that if r is a rotation, then the cofactor of r is the same as r. This is what we saw before. So if we look at the following identity, if we do the divergence of the cofactor of our particular gradient like this, minus the gradient itself, then this thing just vanishes and we end up having, this is just the Laplacian of u. By that I mean the Laplacian of each coordinate. So every time we write divergence of the matrix, we mean divergence of each row, and therefore this is a vector equation. So this is divergence of the first row of this matrix is Laplacian of the first coordinate, divergence of the second row is Laplacian of the second coordinate. Yeah? Oh, but there's a minus sign. So we have this sort of trivial-ish equation, yeah? And we also know that the closer the gradient is to being in space of rotations, the more it is like, it is the case that this thing, the cofactor of the gradient minus the gradient, is close to 0. If it actually was in the space of rotations, then it would be 0, right? So the left-hand side, the stuff inside the brackets, is in an integral sense, in an LP sense, sort of small, yeah? So we don't have a solution of the Laplacian, but we have something which on the left-hand side is relatively small. And that gives us a kind of hint of what we're going to do. So we're going to do the following. We're going to say, so we're going to make our domain very convenient. Let's make it just a ball. So omega is just a ball, just so that we have a nice boundary. And then take a function z that solves the following. That Laplacian of z is equal to minus the divergence of this thing, like this, okay, and z is equal to 0 on the boundary of the ball, like this. Now, you might not be comfortable about why such a thing exists, and this is something I don't want to go into too much. So if you do a basic course on PDE or function analysis, you can learn about why this exists. This is a linear PDE. Once we have u and it's smooth, and this thing is just some function, so we're just asking to be able to solve Laplacian equals some right-hand side with 0 on the boundary. And this is a relatively easy PDE to solve by various methods. So assuming we can find such a z, let's just take such a z, okay? Then what's the point of it? Well, the point is we're going to take z away from u, and that's going to strip away the right-hand side here. So the remainder of the thing, after we define a new function, so we're going to define this time I will call it w. We'll define w to be equal to u minus z, and then if we take Laplacian of w, then it's going to be Laplacian of u minus Laplacian of z, and Laplacian of u and Laplacian of z are the same, so this thing will be equal to 0. So we'll have actually a harmonic function u in the sense that both coordinates of w will be harmonic. Yeah? But this won't be any good to us unless we actually have that what we're doing when we take away z is not changing u too much. All right, so we'd rather work with W because then it'll be harmonic. But again, this is only valid to do if Z is actually small. So we claim it's actually small. So claim Z is small. Specifically, the gradient of Z is small. And we can see this by testing the equation that Z solves. So this is a very typical method in PDE. So notice the following thing. So if we take the divergence of a gradient of a function times some scalar valued function phi, then that thing is Laplacian of this function times phi plus the gradient of phi dot the gradient of phi, where f is something from, say, Rn to R, and phi is a test function, again from Rn to R. Do you want me to write that out? Should we just see that? Because if we have divergence of f comma 1, first coordinate, f comma 2, second coordinate, f comma n, sorry, f comma 1, phi, f comma 2, phi, and so on, then the partials hit the f comma 1, and then the same partial will hit the phi, right? So then this will give us this sum of terms, say j is equal to 1 to n of f comma j, phi comma j, plus f comma j phi, right? Which gives us this. Yeah? Everybody with me? Yeah? So this is a very convenient thing because when we have this PDE here, we are going to take this integral like this of, we're going to multiply both sides by z and multiply through. So when I say multiply by z, I'm actually meaning dot product because everything is vector valued. But we're just going to work with one component at a time. Yeah? So for each component, we have a function from R2 to R, and therefore it's exactly the expression of the form like this, Laplacian times a scalar value test function, when the scalar value test function is the z1 and Laplacian of z1, yeah? And then the next row is Laplacian of z2 times z2, yeah? And then what do we know? We know that we can integrate over omega. So if you look at this kind of little identity, if phi is equal to 0 on the boundary of our region, then the divergence of this thing is going to be equal to 0 by the divergence theorem. So the integral of omega of the divergence of gradient f of phi is equal to 0, just because the divergence theorem, we take the dot product of this thing with the gradient, with the outward pointing unit normal of this, right? But since phi is 0 on the boundary, this is 0. Yeah? Again, nod your head if you'll. Give me a thumbs up if that's making sense to you. Okay, let's write it out. So what is the divergence? So are you guys happy that when we integrate this thing, it's equal to 0? Just tell me if you're not, because we'll just write it out. I guess your silence means you're not, so let's just see it. So if we just look at this thing, so the integral of omega of the divergence of gradient of f of phi dx by the divergence theorem is just the integral around the boundary of omega of this vector field dot product the outward pointing unit normal like this, and it's the height one-dimensional integral like this. Yeah? But phi is 0 on the boundary, so this vector field is 0, so this thing is definitely 0. Cool. All right, so we have this is equal to 0, but it's also equal to this identity, right? So let me put it over here. So then this implies that the integral of gradient of f phi dx is equal to minus the integral of gradient of phi dot gradient of f dot gradient of phi. Yeah? And this is a common trick in it, which we do in PDEs all the time. And that's what we're going to apply to this thing here. So this thing, is, well, let's put a minus sign here. This thing is also equal to the integral of the gradient squared. Remember, this is just a ball, which I took to be a ball just because I have a nice boundary. Like this, But it's also equal to this stuff right here. It's also equal to the integral of the divergence of the cofactor of this guy times z, vz. Yeah, because that's how we defined it. Yeah, we have a minus sign here, so it's equal to this. Yeah. And then we're gonna do the same thing of putting the divergence on the other side, because it's the divergence, so it's the sum of these partials. K equals 1 up to n, the partial k of this thing times z1, and if we have the partial of this thing times z1 like this, then that's equal to 0. Right, so then this thing, let me raise the board somewhere. This is meant as a vector identity, so this is divergence of the first row times the first coordinate, so I should have a dot here, I guess, and then divergence of the second row times the second coordinate. And what do we have here? So let's just write it out like this. So we have divergence of this thing. I'm going to write 1 for the first row, and then times z1 dx, and then that is the sum of all these partials, the sum k equals 1 up to n of the kth partial of this guy right here, like this, z1 dx. But then we can put the partial on the other side because this guy is got 0 on the boundary. So when we consider the integral of the partial of this guy, so this is the partial of the kth component of the first row. So how do I write that? I'm going to write that like 1k. So it's the first row and the kth component of it. So if we take the partial of first row, the kth component, times z1 like this, then the integral of this is equal to 0 because this is 0 on the boundary. Yeah, if we have the integral of a partial derivative of a function which is 0 on the boundary, we can just integrate in that direction across lines, and we'll just end up with nothing. Yeah? It's also just a special case of the divergence theorem when we take the vector field just to have one coordinate. Is this making sense, people? Speak up if it isn't, because I'll just add more details. This is not a scalar. Yeah, this thing here is I did things for scalars, but these things are not scalars. But these equations mean I have vector equations. I have the first row and the second row holding true. So Laplacian of z is vector valued. It's got components z1, z2. It means Laplacian of z1 times z1, Laplacian of z2 times z2. Yeah? And this guy means the divergence of the first row dot product times Z1, divergence of the second row times Z2. Yeah? So that's what I'm trying to indicate here. And I agree the notation's looking ugly. So I'm putting everything, this square bracket, the 1, means this thing here. Everything in this bracket is this. And the 1 indicates I'm just doing the first row. Yeah? So then it's times Z1 here. So, yeah? And then this thing, it's the divergence of the first row. So this indicates the first row and then the kth entry. So it's the partial of the first row kth entry. Again, still times Z1. Yeah? Cool. And then what this thing is I'm trying to convince you that if we have some function multiplied by another function, which is 0 on the boundary, and then we integrate the partial, then it's equal to 0. And it's equal to 0 because if this is a domain like this, let's take lines in the kth direction, then this integral can be integrated along each one of these lines by Fubini. Yeah? And along each line, we just apply the fundamental theorem. So we start here, we end here, and the value is the same because it's 0. Is everybody with me? The moral is, from this line, we can put the partial on the other thing with a minus sign. So then we're going to have a minus the integral of the sum from k equals 1 up to n. First row, kth entry, and then z1, comma k. Yeah? But then this is going to be nothing other than the dot product of, or the integral of the dot product of the first row, dot product, the gradient of the first entry, Z1, like this. Yeah? Cool. And that's just for the first component here. Yeah? So if I do this for the second component too, what do I have? I'll have that this thing is equal to minus the integral, I should put the domain everywhere, of the cofactor of gradient of u minus u dot product the gradient of z dz, like this, because that's what we saw for the first row. It's also true for the second row, and then that's the dot product of matrices that we get when we dot product all the entries as if they were vectors. Okay, so the moral is that this is the equation we want, and it follows by doing this integration by parts a second time. All right, how do you people feel? Is this making sense? Kind of? Yeah? Speak up, because I have to erase the board, and then these details will be lost. But this is the equation we wanted to get to. So if you have any doubts about it, speak up before it all goes. Everybody happy? Yeah. Okay. Where we had our function u, I'm going to go into R2 in our case. We took z such that, writing words, such that Laplacian of z was equal to minus the divergence of the cofactor of u minus u, like this. And from that, we have this identity that the integral of the gradient of z squared dz was minus the integral of the cofactor of du minus du dot product gradient of z, like this. Okay. I should write dx, not dz. That's where we were. And my claim was that this was going to allow us to show that the gradient of z is actually small. Looking at this, do you see any reason why that might be true? Very good. So we are taking the gradient of u, which lives around here, close to the set of rotations, right? And if it actually was on the set of rotations, then this thing would be equal to 0. Yeah? So this thing is just some algebraic expression. Yeah? This is just an algebraic expression. So notice, let's give it a name. So let P of A be this thing, say it's the absolute value of the cofactor of A minus A itself, like this. Actually, let's square it just to have a nicer expression. Yeah. Then this is just a purely algebraic expression. Yeah. It's an algebraic expression. It's a polynomial of these entries. Yeah. And so P of R equals 0 for all R belonging to space of rotations, like this. Yeah. So as we move away from the space of rotations, then this being a polynomial is gonna grow, but it's not gonna grow too fast. It's gonna grow in a kind of controlled way. And we're making the assumption that the gradient is bounded, so it's not gonna go off to infinity. So this is a polynomial, but we don't care what degree of polynomial it is, because it's actually not getting that far towards infinity. So morally, this is really kind of a nice expression, and it's not too hard to see that P of A will be bounded by some constant times the distance squared of the gradient away from the space of rotations, like this. And it's a little bit of a calculation to see this, but we can just see this. This turns out to be true. So both the right hands, this is 0 when this is 0. And the issue is how fast do they grow. And this thing grows at the same rate as the distance squared. So if we just took away this thing just grows at the distance away from, which is not too hard to see because it's kind of like a linear expression at this point. Yeah. Cool. So looking at this thing, looking at this thing. So Josh said that this is kind of small. Keep going with the argument. How does that help us? We have that this thing. If we apply Cauchy-Schwarz to this stuff right here, this is less than. So let's go to constant, but omega of a factor of u squared dx like this. Yeah? And then this thing is just this thing squared. Yeah? So we can divide through by both sides. Oh, I missed the half here. Right? So dividing through by both sides, then this thing implies this. And now I'm just going to put, I can put P, this is how I define P, but P is controlled by the distance, so I'm just going to write the distance squared of the gradient, this thing, 1 over 2. Yeah? And our hypothesis is that this thing is small, so let's actually give this a name. So we're going to let epsilon be the integral of the distance of the gradient away from rotations (1 over 2). So the L2 distance of the gradient away from the space of rotations. So then this thing is less than c times epsilon. Yeah. So our mission is to ultimately show that on some inner sub-region of the ball, the gradient of u is close with this same norm, the L2 norm, the gradient is close to within epsilon of a fixed gradient. Yeah? So we have to get things back in terms of epsilon. But what we've learned is that this thing here, this z that we've stripped away, isn't going to mess with us because the L2 norm of z is controlled by epsilon. Yeah? Are you people happy when I say things like L2 norms? Have you seen that kind of thing before? So Josh has. What about everybody else? Okay, so this trick is very good for us because what we have left, so since you know L2 notation, what we've learned that the difference between the gradient of u and the gradient of w in L2, omega is less than epsilon because w is just the difference between them. Yeah, and the L2 norm of the gradient of z is less than epsilon. So we have the same hypothesis for w as we had before. So this hypothesis that the L2 distance of the gradient of u away from rotations is equal to epsilon. So now we have the same hypothesis, but now for this much more convenient function, w. So I've been writing gradient like this, so I should be consistent. Yeah? Cool. But we are much happier dealing with w because w is harmonic, right? W is harmonic. So w satisfies this very convenient equation. So recall that when we took the Laplacian of the gradient of w squared, this thing was just equal to the second gradient of w, like this, just because it's Laplacian. This is just a result of doing the differentiation on the, just doing the product where we do the differentiation once, then do it a second time. We have a term like this, then a term which is like the gradient of w dot product, the gradient of Laplacian of w, the Laplacian of w is 0. Remember this? So in general, Laplacian of, let's give ourselves another function, gradient of q squared is equal to gradient of q dot product, gradient of Laplacian of q plus the second gradient of q squared, like this. This is the identity we just wrote out before. Yeah. So if we have something which is harmonic, this thing is vanishing, so we just have this. Yeah. Cool. But this thing right here is something which is fairly well controlled because we have that this guy is reasonably close to being inside the space of rotations, right? So that means this matrix over here is one which is reasonably close to being a constant value. Yeah? It's reasonably close to being a constant value. So what we do is take some smooth function phi, which is a scalar valued function. So I'm going to write like this. I'm going to write C, which means it's got compact support. It's on the ball, such that phi is equal to 1 on the half ball. The ball of radius 1/2. Okay, and we can find such a function. So just on the real line, it would be something which looks like that. It's a bump, and it goes flat, it goes down like this. Yeah? And we're going to test this equation here with this guy, Laplacian of times r phi is equal to integral of this thing squared w phi dx. And my claim is that we can put the Laplacian onto this other thing, this test function phi, by integrating by parts. And why so? So this thing, what's the Laplacian? The Laplacian is divergence of the gradient of this entire expression like this. Yeah. Oops. Without this thing on the test function like this. Divergence of the gradient of this thing times this test function. But if we look at this thing, if instead we considered divergence of this guy and phi like this, then this thing would be equal to 0. Yeah? This thing would be equal to 0, again because of the divergence theorem, because phi has got compact support. Yeah? Which means that this thing is equal to the divergence of the thing inside the brackets times phi plus the integral of the thing inside the brackets dot product the gradient of phi. So this is the same stuff we did before. Yeah? So that allows us to write divergence of this test function as the thing dot product with the gradient of the test function with a minus sign. So let's do that. So that's integral of minus the gradient of this thing dot product this thing. Yeah. And we're going to take the test function to be such that since it's got compact support, then its gradient is actually also going to vanish on the boundary. Yeah. So in the sideways picture, I chose it like this. So we can set this up so it's gradient vanishes on the boundary too, which means we can do the same trick and we can put this gradient onto this side by another integration by parts. Yeah? And that gives us back another minus sign, so then we have this. And now I've got dot product gradient of this thing, dx, like this. That's right, yeah, Laplacian, because we put the other gradient on the other side, and then we have Laplacian. Yeah? This one? This one? This one? Ah, okay. So this is a pointwise identity that's just true because W is harmonic. Yeah? Yeah, that's this thing we saw before. Yeah? Yeah. No, don't apologize. This is exactly what I want. I want you guys to pull me back at every stage. So it's pointwise true. So when you multiply by a test function and integrate, it's definitely true. Integration by parts is the rest. Yeah. Cool. Everybody happy? Everybody good? Cool. All right. So we are almost there. At this line right here, we can also stick in a number. And the number we're going to stick in is 2. So what I mean is this is also, everything's always, it's compact support, so I don't care. So this is also the same as integral of gradient of w squared minus 2 Do I need dot product? In this case, I don't need dot product because at this stage, this is a scalar, so now I just have this thing like this. And why so? Well, if we just integrate something of compact support, Laplacian of something of compact support over omega, then that thing will be 0, because what is Laplacian? Laplacian is divergence of the gradient and the gradient of phi has got compact support. So as we integrate this thing over the entire domain, then divergence of this thing is just the dot product of this vector field around the boundary, but this vector field vanishes because gradient of phi has got compact support. Yeah? So I can stick in this 2 like this. Are you all with me here? Thumbs up if so. Speak up. Yep. Yep. Are you happy with y though? Does that make sense to you? Yeah? Cool. So why did I do that? Why did I bother to stick this 2 in? So what are we trying to do ultimately? Look at this chain of stuff. So we have that we have some test function here, okay, which is identical to 1.5 ball, like this. It's equal to this thing, yeah. And then we put the Laplacian on the other side, like this thing, and then we stuck in a 2, yeah. And then mimicking what we were doing before when we had the absolute case, how did we profit from the identity that this thing was equal to this thing? How did we profit when we had the absolute version, when the differential inclusion was exactly in the space of rotations? So if W is such that the gradient's exactly in the space of rotations, what does this line tell you? Well, if W is exactly in the space of rotations, what is this thing right here? It's a constant. It's not 0. So the gradient's in the space of rotations, right? So this is just the norm of the gradient squared. If it's in the space of rotations, what's the norm of the gradient? So if R belongs to two-dimensional rotations, what is the norm of R? If you take all the entries squared, square root it, what do you get? What do you get? 2. You got 2, huh? Yeah. Cool. So when you're close to the space of rotations, then the norm of your gradient should be close to 2. And the closer you are to the space of rotations, the closer you are to having the norm of the gradient is 2. Yeah? Do you all see what I mean? So, I'm running out of space. I want to keep these equations all in the same place. What that means is that we can control this final thing here by something involving the norm of the gradient. And that's what I'm about to show you. So it's a bit more algebra, but it's not too hard to see that given a matrix A inside M 2 by 2, which is not too far away from infinity, we have that the norm the norm of the matrix squared the norm of the matrix squared minus 2 is controlled by some constant of the distance of the matrix away from the space of rotations. And it's the same argument as before. So when A is a rotation, this is identically equal to, this should probably be squared. No, this is fine, because this thing is equal to the difference of two squares, so it's going to be linear in terms of the way it's growing away. Okay, I'm going to keep it this way. So these things are equal to 0 if A is inside the space of rotations, and then it's the issue of how quickly do they grow when you're away from the space of rotations. I'm going to write it anyway. So this is the same as A minus square root of 2 times A plus square root of 2. And as you go away from the space of rotations, then this thing is growing linearly and this thing is growing linearly. And that's why it's true, because we don't care about too far away from the space of rotations because we're assuming the gradient is bounded. Cool. So then this thing over here is controlled by the actual L1 norm, which is controlled by the L2 norm. So it's controlled by integral of the distance of the gradient of W from rotations squared 1 over 2 times this thing, Laplacian of phi squared dx 1 over 2. I don't care about this thing, it's just a constant, it's just this bump function. So this is just less than some constant times this quantity epsilon again. Yeah. So going back to where we started, oh, and this is wrong because this is a square right here, and this is a square right here. So going back to where we started, we have that this thing squared times our test function is less than epsilon. So on a small ball, or a ball of size 1/2, we actually have the good control that we wanted. So this implies that on the integral of ball of size 1 over 2, the integral of the gradient, second gradient of W squared dx is less than a constant times epsilon, like this. Putting all these things together, because our test function is identical to 1 on the ball of size 1/2. I think that's, here we go, from right here. Yeah, so from here, going back through this stuff is all less than c times epsilon. This is a positive quantity. Everybody with me? Yeah. So now we have some real progress. So let's take the square root of both sides. We have that second gradient is square root of epsilon away from an actual, from being actually 0. So look, this is space of rotations. We stripped off z to end up with W. W had the same property, that it lived close to the space of rotations with L2 error epsilon, but it also has this cool property here. So let's put a square root around both sides like this. Yeah? So that means that this guy, its L2 norm is less than square root of epsilon. Yeah? And I claim that is so strong, it's actually going to allow us to say that W is within square root of epsilon of one particular rotation. Why is that strong enough for this to be true? I mean, if we had this on the real line, then that would definitely be true, right? If this was a one-dimensional thing, that would be true, just by the fundamental theorem of calculus. Yeah? But I claim this thing means on a ball of size 1/4, say, we actually have that the gradient of W is within square root of epsilon of some fixed rotation R0. Why is that the case? So I'm going to erase the board. You guys think about this. Let's leave it on that point. So look at where we left off, and then think about this over the weekend, and then think about how we can conclude this thing I claimed that in a ball of radius a quarter, then around 0, then the gradient of W is actually L infinity close to a fixed rotation. Yeah? Think about how that's true if we just had a one-dimensional domain by the fundamental theorem of calculus, and then how that isn't just generally true in higher when we have more than a one-dimensional thing, but we have other things in play. U is harmonic. Sorry, W is harmonic. Yeah? And then see how you can actually get that. Yeah? See you all on Monday.